Hey class, today's lesson starts with a warm-up, so please pause the video now and complete the warm-up. You can tune back in when you're finished. Alright, so thanks for giving the warm-up a try. I know it's been a little while since we've done linear functions and written equations in slope-intercept form, so hopefully that came back to you pretty quickly. As you can see, I used the general format y equals mx plus b. Well, they already gave me the slope, so I just plugged the slope in for m, which was 3, and then I used the point and the slope and plugged into y equals mx plus b to solve for b. And that turned out to be a y-intercept of 50. So y equals 3x plus 50 is an equation that describes the line that will pass through 50, 200, and has a slope of 3. In this lesson, lesson 9.2, we will be looking at what are called piecewise functions. And when we talk about piece, we're not talking about, you know, the peace sign, although, boy, it would be great if we could help promote world peace through mathematics. Notice the word piece is spelled like a piece of candy or a piece of cake or something like that. And so when we say, we talk about piecewise functions, we mean a function that is a combination of one or more functions. So in other words, it's cut up into pieces. We can't describe the function with just a single, whether it be linear or quadratic or cubic function. Instead, it's split up into a combination of one or more functions. And the rule for a piecewise function is different for different parts or different pieces of the domain. Here's an instance of a piecewise function. So you go to the movie, a movie ticket. Movie ticket prices are often different for different age groups. So the function for a movie ticket prices would assign a different value, or ticket price, for each domain interval or age group. So we actually say that it has different equations for different parts of the domain. Now that movie ticket example that I talked about, that's actually what's called a step function. Now the reason why we call it a step function is because when we graph this piecewise function, it actually gives the appearance of like stair steps. And actually that movie ticket example, I have a step function here for that movie ticket example. So basically here's how I would interpret this, except for these would have to say dollars. So let's say that was the movie representation. What it would mean is this. If you are between 0, in other words, just born, and but under 13 years old, you'll pay $5 to get into the movie. But if you're 13 up to just under 55, you'll pay $9 for a movie ticket. And if you're over 55, so if you're 55 or over, which I guess they would consider to be a senior citizen, although I don't think that's a senior citizen, that's pretty young, but then your price of your ticket is only $6.50. So if I were to graph something like this, this is what it would look like. So if you are under 13 years old, you're going to pay $5. So on the graph, that would be here at $5. If this is the dollar price for the ticket, you would have a constant rate of $5 as long as you're below 13 years old. So when you get to 13 years old, you actually have to jump up to the higher price. So we don't want to include that point, and so we're going to put an open dot on that endpoint there, so to indicate that we're not including 13, but anything before that. And of course, you know, you can't actually be 0 years old, so we'd put an open dot there. So that graph would be this, you know, this constant rate of 13 or $5 for up to 13 years old, but not including 13 years old. So when you have a less than sign or a greater than sign, you're going to use open dots to show that on a step graph. If you have a less than or equal to or greater than or equal to, you're going to use a filled dot. So this next interval, which is that when you're between 13 and 55, well, that actually is going to have a filled dot at 13, and that's way up here at $9, so they're charging you $9. And so at 13, you'd pay $9, and then all the way up to, but not including 55. So we'd put an open dot on that end because, again, there's this less than sign at 55. And then starting at 55, the price is going to drop down to $6.50, so that would maybe be right around here, and that's going to be the price for any age at 55 or above. So that's why they call this a step function, because it looks like a series of steps. Lots of real life situations can be represented with step functions, which are piecewise functions because it's made up of a bunch of pieces that are all these constant functions. Here's an example of another application that utilizes a step function. So it says create a table and a verbal description to represent the graph. Well, we've done we have the graph here, and so we want to describe the graph in a table and also verbally. So that goes along with our multiple representations of functions from the prior lesson. So you can see this graph shows prices of mixed nuts over different amounts that somebody might purchase. So if you're purchasing, and you can tell from the graph here by looking at this piece of the graph, that it's $8 if you're buying less than 2 pounds. So I might have written this table a little bit differently. Like I might have put here in the table, I might have said for, let's say, your weight in pounds, say W. If it were less than 2 pounds, that's another way to say it, but I guess they did the 0 to 1.99, but I would say if it's less than 2, then it's at $8. So then the next interval would be starting at 2 pounds, but ending just before 5 pounds. So in other words, if the weight was less than 5, but greater than or equal to 2 pounds, then they only charge you $6 a pound. So they're giving you this bulk discount, cheaper price because you're buying more mixed nuts. And then finally, the price drops down to its lowest point of $5 when you buy 5 or more pounds. So when the weight is greater than or equal to 5 pounds. So here's how I describe this verbally. I just sort of looked at the graph and described what I saw. And I said if you are purchasing under 2 pounds of mixed nuts, the cost will be $8 per pound. If you're buying between 2 and 5 pounds, the price is $6 a pound. And if you're purchasing 5 or more pounds, the price is only $5 per pound. So that seems easy enough, but you have to just kind of keep in mind these key things. First of all, these intervals, where do they break? So if that endpoint is included, you have to use a solid dot on your step graph. And if it's not included, then you have to use an open dot. So again, less thans and greater thans are associated with open dots, and greater than or equal to or less than or equal to with filled dots. Let's go ahead and turn the page. So I'd like this next example to be a you try question. So I'd like you to create a table and a verbal description to represent this graph about the golf greens fees at different times of the day. So please pause the video now and create the table and write a verbal description of the golf greens fees. Okay, so here's how I interpreted this graph in the table. I thought before noon, and I guess you could have said for time less than 12 p.m., but I wrote in words, so before noon. The cost was, I approximated that to be about $28. It looked like the scaling on the vertical axis was by threes, so it had just gone past 27, so I guessed about 28. So then the next interval dropped down in price to only $24, and that was starting at noon, and I know it included noon because the solid dot is actually on that step of the graph. It goes up to just under 4 p.m. So again, the open dot associated with just a less than in my table. And then finally, the lowest price of the day is starting at 4 o'clock, and that's only $12. So I guess they call that like twilight golf. And so my verbal description went something like this. Green fees before noon are $28. Between noon and 4 p.m. you can play for $24. Starting at 4 p.m. greens fees are only $12, so half price. So if I ask you to evaluate this particular function for, say, f of 11 a.m., so f of 11 a.m., you would go to look at the graph, you'd go to 11 a.m., you'd go up to the piece of the graph that is up there at $28. So you'd say, oh, it would cost $28 to golf at 11 a.m. So that's how you could evaluate a step function, is you would utilize that graph or that table. Like if I know 11 a.m., that's before noon, I could also use the table and use that first line of the table because 11 a.m. is before noon, so I know it would be $28. So when we talk about evaluating a piecewise function, if we want to evaluate any piecewise function for a specific x value, we have to find the interval that's listed that contains that x value and plug in your x value for the corresponding rule. So let's take a look at doing some evaluating some piecewise functions. So obviously not every piecewise function is going to be these constant functions or step functions. Sometimes our pieces might be, we might have some pieces of our function that are linear, some pieces that are quadratic. We might have a part that's even a logarithmic graph or exponential growth or something like that. So, you know, the pieces of the graph that might be used to describe the situation over certain intervals, they might be lots and lots of different types of functions. So for example, in example 2a, I have a linear function, so 2x plus 1, that's a linear function, and that describes this function if x is less than or equal to 2. So for any value of x that's less than or equal to 2, this is going to be the function I use. It's a linear function. And if x is greater than 2, I would use the function x squared minus 4, which is a quadratic function. So this particular situation over different intervals could have a linear behavior, and parts of it could have quadratic or parabolic or parabola behavior. So if I were asked to evaluate this piecewise function for x equals -1 and x equals 4, well, first of all, how I write in function notation evaluating x equals -1, it would be like this. So the function's called h, so I could say h of -1, which means I'm going to plug -1 in, and now I got to decide which one I'm going to plug it into. Well, -1 lies in this interval, so I'm going to plug it into the 2x plus 1. So I'll plug that -1 in and evaluate that. So that would give me 2 times -1, which is -2, plus 1 is -1. So h of -1 equals -1. Now if I wanted to instead evaluate for x equals 4, now I'd be doing h of 4. Now I've got to use this interval, because see, 4 is actually greater than 2. So I want to use the function that's associated with this value in this interval. And so I'd use the x squared minus 4 function, and I'd plug that 4 in. So that would give me 4 squared, which is 16, minus 4, which is 12. So h of 4 would be 12. So I had to use the piece of this function that's associated with where my input, my x value, lied in the interval. Let's take a look at example B. Well, this time I can see that what I have here is this function right here. I mean, these are the intervals that go with this, but this is the function itself. And then these over here, these represent the intervals. So if I ask you to evaluate the piecewise function for x equals -1, in other words, I want to know what f of -1 is, well, the first thing I'm going to have to do is figure out where -1 lies in these intervals. Well, I know -1 must be right here between -3 and -6. So it fits in the interval x is greater than or equal to -3 and less than 6. And so I would think normally then I would actually go plug this in, but there's no place to plug it in. It's just a constant function. So that tells me that the output must be 15. So f of -1 would just be 15. Now what about x equals 3? Well, x equals 3 is also in this exact same interval. So f of 3 would be the exact same value. It'd be 15. So here's how we evaluate piecewise functions that are actual equations and also ones that are constant functions. Let's turn the page. So next we're going to look at graphing piecewise functions. So when we graph piecewise functions, these intervals become very, very important. These places where, because that basically is going to tell us what the domain is for our particular piece of the graph that we're trying to represent. So looking at example A, it says graph each function, and they say that g of x is equal to 1/4 x plus 3 if x is less than 0, and -2x plus 3 if x is greater than or equal to 0. Now here's the strategy that I use. The very first thing I always do is I will always draw sort of like a boundary line here where the interval breaks. Notice that the interval breaks right here at 0. So what I do is I go over here to the graph, and on that graph I'm going to put a vertical line down here, which basically is just a reminder, this is where the function's going to change over from that 1/4 x plus 3 to the negative 2x plus 3. Now I like to make a table for piecewise functions, and I make a table with 3 columns, and that's because I have 2 different functions. I have one function that's this 1/4 x plus 3, and I have one that's the negative 2x plus 3. And so I have to have a column for my x's, and then I have a column for each one of the functions. And then I also will go through, and wherever that break value is, see where this 0 was? I'll always kind of circle that point on my table. Now, see, if you look at this table, the values that I start to plug in at -4 and -2, if I were to plug those in, I would only plug them in to the 1/4 x plus 3 because they're in that interval where x is less than 0. So I actually would just cross out these pieces, or these spaces here, because I'm not going to plug -4 into -2x plus 3 because it's outside the interval. And then I'm going to, and the same thing is once I get past that, that point of 0, I'm not going to plug like 2 and 4 into 1/4 x plus 3 because it's outside the interval. So I'll like cross those out as well. So basically, I'm going to find, or I'm going to plug in for -4, -2, and 0 into this first column, and then I'm going to plug in for 0, 2, and 4 to the second column. Now, I also kind of look at these inequalities. So notice the first interval ends, or that first function ends at 0, and it doesn't include 0. So what I do is I put kind of like a parenthesis around in this spot in the table, because I know that actually, when I plot that point, I'm going to put an open dot there. Now the other one is fine, so I'm going to just, because that's where on the other interval here, I have a or equal to, so I'm actually going to be able to plot that point with a solid dot. So then I just start plugging in, and I just plug in, so I'll plug the -4 into the 1/4 x plus 3. So let's see, 1/4 times -4 is -1 plus 3 is 2. So this turns out to be 2. And then -2, if I plug that in, then I get a negative a half, and then add 3, which is 2.5. And then if I plugged 0 in, 0 times 1/4 is 0 plus 3 is 3. So I'm going to go over here and plot these points to graph that first part of the function. So I'm going to plot -4, 2. So here's at -4, and then I go up to 2. So there's a point there. And then I've got -2 and 2.5. So that would be about here. And then I have 0, 3. Well, remember at 3, I want to use an open dot there because it's not actually included. So this piece of the graph is going to be a linear function, but it's going to get cut right off right there at that boundary line, right where the interval changes over to the next function. So I've got that part done. So now I'm going to jump over here and do the other part. So now I'm going to plug 0 in, but this time I'm going to plug it into the other function. So -2 times 0 is 0 plus 3 is 3. So that means I'm actually going to have a solid dot right over where that other one was an open dot. Then I plug 2 in. -4 times 2 is -4 plus 3 is -1. And then I plug 4 in. 4 times -2 is -8 plus 3 is -5. So I'm going to plot these points for that graph. So at 0, it's going to be 3. This time that's a solid dot. That's why I used a different color here. So you can see that the solid dot is the blue graph, the one that's going to be to the right. And at 2, it's -1. And at 4, it's -5, way down here. So this is also a linear graph. It's just much steeper, and it's declining. It's a negatively sloped line. So when I connect those points, there's my piecewise function. And at any given point, there is only one point that's represented on this graph. So it is a function. It will pass the vertical line test. The only place where you might be concerned about it is at that point where they overlap. But remember the purple graph, the 1/4 x plus 3, that point it's going right up to that, but it doesn't include that point. So we're safe here. It passes the vertical line test. It's a function. So let's try another one. Now this one looks a little more complicated. So g of x is actually comprised of 3 separate pieces. So notice that that the intervals change at 0. Here's where they change at 0. And then they change again at 4. So I'm actually going to put 2 vertical lines in here to kind of break this up. This is going to get broken up right here at 0. And then the graph is going to switch over to another one at 4. So I put these lines in here to remind myself that this is where the breaks are going to occur. So I'm actually going to have 3 regions where I'm going to graph these. On the left of this one at 0, so like in other words, over in this section here is going to be this graph. In between these two is going to be this graph, and then to the right is going to be this graph. So again, the other thing that I do is I'll come down here in the table, and I create a table for these because we're going to have, let's see, 3 functions. We're going to have x squared minus 3, so that's a quadratic piece. Then there's going to be a half x minus 3, and that's linear. And then there's going to be another quadratic part, x minus 4 squared minus 1. And so that's a third piece. And so I know that these key places where it changes over are going to happen at 0 and at 4. So I know that's kind of my break point. And then when I think about where the open dots are going to be, well, there's going to be an open dot because of this right here. Okay, there's going to be an open dot right there at 0 for that first function. So I'm going to put my little parentheses here to remind myself that's going to be an open dot. So you could even, if you put a little open dot, it might look like a 0, so maybe it's safer to do something like this. And then there's going to be an open dot again right here when the second function ends at 4. So this one's going to be an open dot there. And now I'm ready to start plugging in values so I know for this first function I'm only going to plug in values that are less than 0. So once I get past 0, so like here and here and here and here and here and here, I'm not going to plug in there because they're outside of the interval. So I'm going to take a look at just that. Now in the second function, it's between 0 and 4. So before that I cross out, and after that I cross out, and I'm only going to plug in those values between 0 and 4 for that one. And then finally the other one only exists after 4, or starting at 4 and after, so I'm going to cross out anything that's leading up to 4, so just before 4, because I'm only going to put values 4 and up in for that one. So that just narrows it down. I mean, then I've got less to do. So let's see, if I plug negative 4 in, negative 4 squared is 16, minus 3 is 13. So one of my points is negative 4, 13 on this graph. Then I plug in negative 2, so if I plug negative 2 in and I square it, that's positive 4, minus 3 is 1. And then plug in 0, of course I'm going to have an open dot there, but plug in 0, 0 squared is 0, minus 3 is negative 3. So now I'm going to plot those points, and I know it's supposed to be kind of part of a parabola. So if I plot negative 4, let's see, that's negative 4 and 13, that's going to be way off the graph, but I can kind of approximate it. Maybe like right up there. And then I have negative 2 and 1, which is right there. And then finally I have 0, negative 3, and at 0, negative 3, I'm going to have an open dot right there. So I know this is supposed to be a curve, so I'm going to see if I can kind of give it that appearance that it's part of a parabola. And again, then my graph's going to cut right off there, and I'm not going to do anything more with that function. Now I'm going to jump over to the next function. So now as I'm filling out that function, I start plugging in 0. So I plug in 0 to 1/2 x minus 3, so 1/2 times 0 is 0, minus 3 is negative 3. Then I plug in 1. 1/2 times 1 is a half, minus 3 is negative 2.5, or negative 2.5. Then I plug in 2, and I get negative 2, because 2 times a half is 1. 1 minus 3 is negative 2. And then finally I plug in 3, and that gives me a 1.5 minus 3, which is negative 1.5. And then, actually I forgot one more. Final one, plug in 4. 4 times a half is 2, minus 3 is 1. So now I'm going to plot those points. So I plot negative 1. So I'm going to plot the point 0, negative 3. So this time I'm going to use a solid dot. Helps if I have color. I know sometimes when you're not using color it's going to be hard to see that. So just do your best to show that, one of them is a fill dot, one is open. Then at 1 it's negative 2.5. So there's 1, and negative 2.5 would be about there. And then 2 and negative 2, so right there. And 3 and negative 1.5 right there. And 4 and negative 1, but that's an open dot there. So then I just got this little linear piece right in there. So finally I'm going to go on to my last part of this piecewise function. And I'm going to start plugging in values starting at 4. So I plug 4 in, into x minus 4 squared minus 1. So if I plug 4 in, that's 4 minus 4, that's 0. 0 squared is 0, minus 1 is negative 1. If I plug 6 in, 6 minus 4 is 2, 2 squared is 4, 4 minus 1 is 3. And then if I plug 8 in, 8 minus 4 is 4, 4 squared is 16, 16 minus 1 is 15. Well, I'm not going to be able to fit that one on the graph, but I can estimate it. So now I plot the points 4 and negative 1, and so that's going to actually be right in the center of that other one. They won't always connect in this way, but in a lot of cases they will. So, and then at 6, it's 3, so there was 5, 6, 1, 2, 3, and remember this is a parabola again, so it's going to be a curve. And then 8, I'd have to go way up here, even past 13, maybe right up here, and so I got to curve that up. I know that that's part of a parabola, so there we go. So basically it looks like, almost like a parabola, but part of that graph, actually, they pulled out part of that curved part of the parabola and threw in a line to kind of split it up in the middle there. So using this strategy of really kind of analyzing the breakpoints in this function and, you know, drawing these boundary lines and you know, creating a table in the way that I showed you, it really is probably the best strategy I've seen for this, because otherwise you're just kind of, randomly picking points. You don't, know where your graphs are supposed to connect or where do you stop. And so this is really a nice planned out strategy that really will work for any of our piecewise functions. Let's go ahead and turn the page. So I've left you a couple easy ones, and I would like to designate these as our U-try problems. So please pause the video now and complete example C and example D, and once you've completed them, you can tune back in and check to see how you did. So pause the video now. All right, so thanks for giving those a try. Example C, hopefully you noticed, was a step function. It just was a constant function, so really no need to make a table there. Just the breakpoint at -1, and then you have two horizontal lines, one that's to the left and one that's to the right. One that's to the left is up at 4, and the one that's to the right is down at -2. And again, notice I have an open dot there on that lower horizontal line because it's x is greater than -1 is the domain for that one. And then in D, I thought it was a good idea to make a table. So this is the table that I made, and I followed the same strategy I talked about before, putting your boundary line in, and then identifying the points that are actually in the domain that you want to plug into each separate function. And if you need to pause the video now to kind of study this in more depth, if for some reason your graphs don't look like my graphs, then do so. And be sure to make a note if you need to bring anything up in class. So let's turn the page. Okay, so many real-life examples can be represented with piecewise functions, as I mentioned earlier, so it's time we looked at a real-life application. So it says Shelley earns $8 an hour for the first 40 hours that she works. Then she earns $12 an hour for each hour over $40 that she works. Sketch a graph of Shelley's earnings versus the number of hours that she works up to 60 hours. Then write a piecewise function for the graph. So the first thing I think of is, when is this situation changing? Well, it's changing at 40 hours. So if I wanted to actually, plot out some of these points, and I thought about that first, I know that the break point in this graph is going to be at 40 hours. That's where her pay strategy changes over to a different rate. So if I wanted to think about this under 40 hours when she works. So when she works for the hours less than or equal to 40, but greater than 0, of course, because you can't work 0 hours, she gets paid $8 per hour. But if she works for a number of hours over 40, then she gets paid for those hours only that are over $12 an hour. So it's not like if she goes to 41 hours, all of a sudden all those hours are paid at $12. Only the 1 hour additional that she worked. So she got paid $8 per hour for the first 40, but then that final hour she got paid $12. So that's something to really think about. That's going to be kind of tricky as we write a function to describe that. So step 2 says, because the number of hours worked is independent variable, determine the intervals for the function. So we did that. Here are the intervals that we just determined right there. I'm going to put them in our piecewise function. We'll say for hours less than or equal to 40 for our first part of our interval, and then for hours greater than 40. And I guess technically it's for hours less than or equal to 40 and also greater than 0 if you want to get technical with it. That's why our graph, when we graph, it's only going to be in the first quadrant because we can't have negative hours. So, I mean, as long as you kind of recognize that, I guess it's not that big of a deal if we don't put a lower bound on it. So how do we describe the first 40 hours? Well, that's easy enough. The first 40 hours will be $8 times H, meaning the number of hours that she works. Now that second interval, when she gets over 40 hours, well, she's already made, if she's already worked 40 hours, she's already made 8 times 40 hours, or $320. So she's going to get paid $320, and this is for the first 40 hours. Plus, she's going to get paid $12 for every hour over 40. So if we plug in hours, we actually have to, so if the hours is say 41 or 42, then we have to subtract 40 from that. So I might have to move my interval here because it's a little more complicated formula. So my number of hours worked, I have to subtract 40 from it. And the reason why is that first 40 hours is already accounted for right there. Okay, we took the 40 hours and already took them into account. So again, now this is actually describing when we have hours over 40. And this will work because you think about if you worked, say, 42 hours, you'd plug that in, you'd make the $320 for the first 40, plus you'd make $12 for 42 minus 40, or 2 hours more work. And that would calculate out to work out fine. So if we wanted to graph this, we could just calculate some different number of hours she could work. Like she could work 10 hours. If she worked 10 hours, she'd get $80. That would maybe be right around here on the graph. If she worked 20 hours, that would be $160. That might be right around here. If she worked the full 40 hours, it'd be $320, which would be right here on the graph, right on that boundary line, because that's where it changes over. If she worked 0 hours, of course, she gets $0. So you've got a linear function up to there. And then you're still going to have a linear function, but to graph beyond that, so let's say we plotted, I don't know, let's say we put in 50 hours. If we put in 50 hours, so f of 50 would look like this. It would be the $320 already earned plus $12 for 50 minus 40, or 10 more hours. So that's going to be $320 plus 10 times 120, or 120 more dollars. That makes a total of $440. So at 50 here, I'd go plot 440, which would be right about there. And then at 60 hours, I could do the same thing, plug 6. So if I did that, and I just instead put in 60 here instead of 50, then I'd be getting paid for 20 more hours at that rate. So instead of 120, I'd be making an additional 240. And so then that makes 560, so I could plot 60 and 560. So here's about 560. So just notice that that second piece of the graph is just steeper. It's still a line, but it's just a steeper line. So this seems like a good place to stop for today. We will be leaving the next real-life example on the next page as an in class. So we'll designate that, label that as in class, and that's where we'll pick up when we meet again. So I'll see you then.